f from some ball into the complex numbers is holomorphic. Then f has a primitive. On the ball. And I gave you a kind of idea how to start the proof. So what we did was we said, okay, let's make the ball centered on 0, and the radius is unimportant. It's always the same. I mean, it doesn't matter for any of the details of the proof. And if we take any z, then we can create a contour that goes like this, which goes along and then up to our z, and we can call that the contour gamma of z, right? And if we chose a different contour that went up and then along, it would make no difference, because we know that if we integrate around the rectangle, it's equal to 0, because that's the theorem we just learned, right? Just before, yeah, because that's just applying Goursat's theorem for a triangle on breaking up this rectangle like this, yeah? Cool. So we can indeed define such a function. I have a proof over here. What does it? Yeah, let's put proof here. Define, or for any z, define a curve as shown, and then define capital F of z to be the integral over the curve like this. And let's call this zeta. Okay, so and my suggestion for you last time was that you think about how this thing can form a primitive. Did you do that? Do you have any ideas? So we're going to have to show that. So that the limit as h goes to 0, f of z plus h, firstly we want this limit to exist, and we also want it to be equal to little f. Yeah? Any ideas about that? Okay, well, let's take a look. So let's blow up this picture onto a larger scale. So we take our little h going in any direction. Let's say this here is our point z plus h, right? And let's blow up what we see here onto something much bigger. Well, actually, let's just blow up. Okay, let's do this in a couple of stages. Let's put z here, so it's out the way. So this is the point z, and say this is the point z plus h. Okay? So, if we take the contour that gets to z plus h, what does it do? It goes along like this, and then it goes up like this, right? This is this contour. Yeah? And the contour that gives us capital F of z goes along like this, and it goes up like this. Yeah? So, if we just consider this quantity, capital F of z plus h minus capital F of z, okay, then what is that? Well, that is the same as going up like this, yeah, minus the contour that goes up like this, yeah? But minus z is like going down and then across. Yeah? Yeah? Minus z is like going down and across. Yeah? Because we've learned that if we do a contour in the opposite direction, it's minus what it was in the previous direction. Yeah? Cool. So if we go down and across, and then we add f of z plus h to it, it means going across and then up. Yeah? This part here is going to be wiped out because we're going this way and then back across it. Yeah? Do you see what I mean? So what this means is that capital F of z plus h minus z is like what happens when we go down, across, and then up like this. So we integrate little f on this contour. That's exactly what capital F of z plus h minus capital F of z would be. Yeah? And then we could, instead of doing that, we could say, okay, what if we considered the rectangle formed by going across like this? Yeah? Yeah? So if we consider the rectangle formed by going across like this, we know that the integral of little f over the rectangle defined like this is 0. That's the theorem we've discussed. Yeah? So that means that going around like this, yeah, has to be the same as just going like this. Just going like this. Is this picture large enough for you? Shall I make it bigger? Put your thumbs up if you can see it. Okay. So once again, since going around like this, integrating on all these four sides, gives us 0. Yeah. If we just did 3 of those sides, yeah, and then added this side, it's 0. Yeah. Which means those 3 sides is the same as negative this side. Yeah. And negative this blue side is the same as going in the opposite direction. Put your thumbs up if you are with me here. Okay, cool. So when we're doing this contour this contour integral that gives us capital F of z plus h minus capital F of z, instead of going around these 3 sides all the way up to here, we could instead just decide to go from here across and then up to this. That would be the same thing. Yeah? Because once again, going across like this is the same as going like this. Cool. So we have, let's blow it up over here, we have that this thing is equal to what happens when this thing here is z, and we go across like this, and then up like this, to z plus h. Yeah, that's what we've learned. Yeah, so if we integrate on this contour with little f, that's exactly what this thing is. Yeah. Now, consider the rectangle formed by doing this. Yeah. If we go down like this, then integrating over this rectangle with little f gives us 0. That's Goursat's theorem. Yeah. Which means that if we integrate like this, yeah, and then plus this blue side, it's equal to 0. Yeah. Which means minus this blue side is the same as integrating across like this and then up like this. And minus this blue side is the same as going in this direction. Yeah? So what this picture just shows us is that actually this quantity is the same as directly integrating from z to z plus h, yeah, in a line. Yeah? Cool. All right. So what that means is that we can explicitly write out what this thing will be as a nice simple contour. Right? So we've just shown that this thing is equal to the integral of the line segment z to z plus h. And I'm going to put this arrow here. maybe it's not necessary, but just to indicate we're going from z to z plus h, yeah? And f of z, dz. Not z, because we've used zeta. That's what we know. Yeah? Thumbs up if you're with me. Cool. All right. And this thing is an easy thing to calculate because we can just put a parameterization for this little line segment here. So let's say z of t is equal to z plus t times h for t belonging to 0, 1. Yeah? So z of 0 is equal to z, and z of 1 is equal to z plus h. And so this thing, let's call this thing star. So star, we're going to write out this parameterization, is equal to the integral from 0 to 1, f of z of t, z prime of t dt, and let's see what that is. That is the integral from 0 to 1, f of z plus t times h. And then when we take the derivative of this thing, it's very simple. It's just h, right? dt. That's what we get. Yeah? Cool. So that is our thing that we're trying to understand. Let's maybe erase this thing. Doesn't matter. So f of z plus h minus f of z over h. We divide by h. This h is not part of the integral. We just pull it out, right? It's just some complex number. So then this thing is just the same as the integral from 0 to 1 of little f of z plus t times h dt. Yeah? Cool. So if we want to look at the difference between f of z plus h minus f of z over h minus little f of z, okay, well, that's the same as the absolute value of the integral from 0 to 1 of this guy, f of z plus t times h. And now let's just put this f of z right inside like this, okay, dt. Because when we integrate just this fixed complex number, f of z over 0 to 1 with respect to t, it's just f of z. Yeah? So we can just put it inside the integral. Yeah? And let's put the absolute value signs outside like this, or inside like this. We have this plus t times h minus f of z like this, dz. Yeah? Cool. So what is that? What's that quantity here that we're integrating? Well, let's put a little bit of space. So we have z, and we have z plus h, and this thing is just some point along this line as t goes from 0 to 1. Yeah? And f is differentiable. Yeah? F is differentiable, so in particular it's continuous. So as h goes down to 0, yeah, then f of z plus t times h has to tend closer and closer to f itself, right? Yeah, for any t between 0 and 1, right? So again, this thing is just some point along this line. Yeah. So this would be where z plus t times h would be, say, yeah? And since we have continuity, then the difference between little f of z and little f, in fact, inside any ball, right, of radius h is going to go down to 0. That's what continuity means. Yeah? So this entire expression here is going to tend to 0 because we can guarantee that this stuff inside the absolute value signs is less than epsilon. Yeah? So long as we insist that little h is small enough, just by continuity. Yeah? So since this is less than epsilon for every t between 0 and 1, then as we integrate over 0 and 1, the entire thing is less than epsilon. Yeah? So that guarantees that as little h goes down to 0, this quantity has to go down to 0 as well. Yeah? In other words, we have exactly got the limit of this thing is equal to this thing. What did we use? We just used this nice property that we learned that if we integrate around a closed rectangle inside this ball, it's equal to 0. Yeah? And that if we integrate across a triangle, it's equal to 0. We just use Goursat's theorem. Yeah? So Goursat's theorem allowed us to turn this somewhat complicated looking thing, right? Which we went, when we consider f of z plus h minus f of z, it's like going up like this and then plus going down like this, yeah? Yeah? Which we know is the same as going down then up, yeah? Yeah? Which is the same as just going across then up, yeah? Which is the same as just going in a direct line like this. Just by using Goursat's theorem again and again to just reduce it. Yeah? Okay. So after this class is over, a good idea is to just try and draw the pictures to convince yourself of this reduction to understanding f of z plus h minus f of z, yeah? Just in terms of integrating little f from here to here. Convince yourself that it reduces from this to this from these pictures. Okay? Because that's basically the heart of the proof. Yeah? And then this stuff is kind of, once you're here, you know you're in a good shape because you write down the expression and you divide by h, you have exactly this. Yeah? And so this thing minus this thing for sure is going to tend to 0. And you're all set. Cool. So we have that this is true, that any holomorphic function has a primitive on the ball. Huh? Cool. All right. Now I keep saying that complex analysis is calculus in the complex plane, but that it diverges dramatically. What about this theorem? Is there an analog to this theorem when we just consider real valued functions into R? What would be the statement of the analog for real valued functions into R? What's a ball in the real line? So the analog would be if we have a differentiable function in the open interval, it has a primitive. Is that true? Is that true, people? I'm going to erase the board. You guys think about this. Give me an answer before we get going again.